Hello everyone, my name is Harshita Sone. Today we will continue our end same paper solution playlist. Here is the question number 8. A. Compare the decision trees, random forest and boosting, highlighting strength and weakness of each. Basic idea about decision tree, random forest and boosting is a single tree that spreads data into branches to make decisions is called decision tree. An ensemble of many decision trees built on random subsets of data and features is called random forest. Sequentially builds models where each new model corrects errors of previous models is called boosting. So, uh, decision tree, greedy learning, random forest, begging, boosting. Its learning style is boosting. How models are built? So, decision trees built one tree built on whole data set. Random forest, many trees built on random samples and averaged. In boosting, many weak learners added one after another. On the feature of bias, decision tree high bias, random forest lower bias, boosting very lower bias. On the basis of variance, decision tree high variance, random forest low variance, boosting can be high if boosting is overfitted. Overfitting highly prone to overfitting decision tree. Then random forest less prone due to averaging. On the basis of overfitting, boosting can overfit if too many iterations. Now, on the basis of overfitting, highly prone to overfitting a decision tree. On the basis of overfitting, the random forest is less prone due to overaging, and the boosting is can overfit if too many iterations. On the basis of interpretability, the decision tree is very easy to interpret, and random forest is hard to interpret, and boosting is hard to interpret. Accuracy. On the basis of accuracy, decision tree moderate accuracy. Accuracy of decision tree is moderate, and the accuracy of random forest is very high, and the accuracy of boosting is very high accuracy. The speed of decision tree is fast. The speed of random forest is slower. The speed of boosting is slow. Uh, okay. For this is the same for the prediction and training. Robustness on the basis of robustness to noise. Our decision tree is not robust. Random forest is robust, and boosting moderately robust but can learn noise if not regularized. On the basis of handling missing values, a decision tree can handle using surrogate weights, and random forest can handle if individual trees handle missing values. But boosting algorithm handle them well. When to use decision forest? When interpretability is important. And when to use random forest? When accuracy is needed and overfitting must be controlled. When to use boosting? When highest accuracy is needed in complex task competitions. On the basis of weakness, our decision tree overfits easily and it's unstable. Weakness of random forest, it is hard to interpret, slower, large model size. Now the weakness of boosting is risk of overfitting, long training time, complex parameters. Its strength of decision trees, simple to visualize, understand, and fast. Then the strength of random forest is it reduces overfitting, stable and high accuracy, and the strength of boosting, excellent performance, handles complex patterns, works well on imbalanced data. Typical applications of decision tree: simple classification, quick decisions, rules-based systems. Then the typical applications of random forest: finance, healthcare, e-commerce, fraud detection. Now the typical applications of boosting: Kaggle competitions, credit scoring, NLP, image classification. Example algorithm name of decision tree is CART. Classification is regression tree. Random forest algorithm name, random forest classifier, boosting algorithm name, example, ADA first gradient boosting XGBoost light GBM. Now let's come to the part B of question number 8. Show how basic logic gates can be built using single layer neural networks. Compare tables, gate, number of neurons, activation function, back propagation needed. A single layer neural network can implement linearly separable logic gates such as AND, OR, NAND, NOR. These gates can be created using one neuron, weighted inputs, bias, step activation functions. Perspectron calculates y is equals to f w1 x1 plus w2 x2 plus b, where x1 and x2 are the inputs, w1 and w2 are weights, b is bias, f is activation, step activation. AND gate using neuron. Output is 1, only both inputs are 1. Weight and bias. W1 is 1, W2 is 1, B is equals to minus 1.5. Computation. Only when 1 into 1 plus 1 into 1 minus 1.5 is always greater than or equal to 0. Output is 1. A single perceptron works. X1, X2 and N output. When 0, 0, then output will be 0, 0, 1, output will be 0, 1, 0, output will be 0. When 1, 1, the end output will be always 1. Or gate using neuron. Output is 1 when at least one input is 1. Weights and bias. W1 is 1, W2 is 1, B is 0 0.5 minus. Even one input makes the sum greater than or equal to 0. Output is 1. NAND gate using neuron. It is opposite of it and weights and bias. W1 is equal to minus 1, W2 is equal to minus 1 and B is equal to 1.5. Produces 0 only when both inputs are 1. X1, X2 and NAND output. Here 0 0 is 1, 0 1 is 1, 1 0 is 1 and 1 1 is 0. NOR gate using neuron. It is opposite of OR. Weights and bias. W1 is equal to minus 1, W2 is equals to minus 1, B is equals to 0 0.5. It produces 1 only when both inputs are 0. X1 and X2, when 0 0, then output will be 1. Otherwise, uh, in all combination, output will be 0. Here is the table where you can see the neuron counts, example, weights and bias, activation function, linearly separable or not, backdrop needed or not. Thank you so much.